Okay, so we are moving into section 3.2, part 2. So this is covering concept number 2. Energy is transformed in nuclear reactions. This is page 288 in your textbook. So we looked at energy transformations in chemical reactions, and now we're going to focus on nuclear reactions. So this is a bit different from anything we've looked at before, but I'll make sure to go through everything in parts to help you understand. First off, we need to remember that natural background radiation exists all around us. Often we think of nuclear reactions as being man-made and potentially disastrous, like in the movies. But in reality, radiation is naturally occurring all the time. So radiation consists of high energy particles or waves, which are being emitted in a variety of materials. So this is going back to Science 8 and the electromagnetic spectrum. So these are basically all the different forms of radiation that are simply coming from the sun towards us in the form of visible light, radio waves, microwaves, etc. Radioactivity is the release of high energy particles or waves. Being exposed to radioactive materials can be beneficial or harmful. X-rays, radiation therapy, and electricity generation are beneficial. So to some extent, there are obviously some risks to this, but the benefits outweigh the cost. If you're going to be exposed to this radiation over and over and over and over again in a very short period of time, that's obviously not going to be great for you. But a one-off check for, say, a break in your bones is not going to cause problems. On the harmful side, high energy particles and waves damage DNA in our cells. So radiation poisoning is from our DNA being damaged. So there's a video titled, "What Does Harmful Radiation Do to Our Body?" I will have this linked in the schedule as well. But essentially it takes a look at the harmful effects of radiation on our body. Super interesting and will be linked on Teams. So take a moment, pause here, watch this video first, and then you can move on to the rest of this section. So when atoms lose high energy particles and waves, ions or even new atoms can be formed. High energy waves and particles are called radiation when they leave the atom. So while part of the atom, they haven't radiated away, they are not radiation. So radiation is that movement away from the atom. So a brief history for you. Radiation is everywhere, but can be difficult to detect. This is because it's invisible and we cannot see it with our eyes. So X-rays were named X-rays by Röntgen in 1895. And in the same way we use X for an unknown in algebra, it was an unknown at the time 100 years ago. So that's where the term X-ray comes from. Becquerel in 1896 realized that uranium emitted seemingly invisible energy as well. So this was a year later. He used photographic film, which was exposed to these radioactive rocks. It would basically expose the film to produce this kind of green discoloration. So kind of like how photos work, same idea, but the radiation was causing this effect. Marie Curie and her husband Pierre in 1890s named this energy radioactivity. Early discoveries of radiation relied on photographic equipment. So using photographic plates, think back to the first camera where film was very large. It was basically a thick plate that you had to put into a camera. You only got one picture out of it. So this was basically what they were using. And also Marie Curie was one of the first most recognizable female scientists, which is pretty cool. So curium was an element that was named after her. She named polonium after Poland, which was her home country. So obviously she made some major contributions to the field of science. So first female scientist to be widely recognized in Western scientists that paved the way for many future female scientists and male scientists as well. So later, more sophisticated devices such as the Geiger-Müller counter were developed to more precisely measure radioactivity. So a Geiger counter goes beyond using photographic film, putting a plate down and saying, hey, let's see how many lines and dots I can get on this plate. This is where it actually can be quantified. So these are obviously still used today. So again, a couple of short videos for you to watch to give you a bit more background information. So pause here, watch these videos, again, linked on Teams, and then you can continue on with this lesson. So isotopes are one of the most important things we can look at in nuclear reactions because some isotopes are more stable than others. So isotopes are different atoms of the same element, with the difference between the two atoms being in the number of neutrons in the nucleus. So remember, the number of protons is what defines the element. So if we change that, we end up with a completely different element. So we don't want to change that. So proton number does not change. Neutron number, however, can change, and it can add mass to the nucleus, but doesn't actually do anything to the charge because it's neutral. So isotopes have the same number of protons and therefore the same atomic number as each other. So because the atomic number is the number of protons, this doesn't change. They are the same thing. One element will always have the same number of protons. So looking at the bottom here at the example of hydrogen, we have protium is what we think of as our stereotypical hydrogen that we commonly work with. One proton makes up its mass. It has no neutrons. Deuterium has the mass of 2 because of the additional neutron. And then tritium has 1 proton and 2 neutrons, and therefore its overall mass is 3. So if you look at a periodic table, remembering that we kind of mentioned this back in chemistry, your periodic table only goes to 1 decimal place. So our table will say 1.0. But other periodic tables with more decimal places, you might see 1.01. And that 0.01 comes from averaging these different masses of these isotopes. By having different numbers of neutrons, isotopes have different mass numbers. Isotopes of an element have the same symbol and the same atomic number. Only the mass changes, everything else is the same. Mass number refers to the number of protons plus neutrons in an isotope. So for example, if we're looking at boron here, 10.8 is the average mass, but remember that the atomic mass for each isotopes is equal to protons plus neutrons. And that neutron number will vary based on the different isotopes. So let's look at this in a bit more detail. Atomic mass equals the proportional average of the mass numbers of all isotopes in an element. So if we look at boron, which has a mass of 10.8 on the periodic table, 19.9% of boron atoms will have 5 neutrons, and 80.1% will have 6 neutrons. All of them, because they are boron, have 5 protons. This does not change. So the atomic number does not change. The proton number does not change. So 20% have 5 neutrons, therefore an overall mass of 10. 80% have 6 neutrons, so an overall mass of 11. So if you were to take 20% of 10 plus 80% of 11, that would give us the 10.8, which is the number on the periodic table. So what that calculation looks like, remembering when we're working with percents, we need to convert it to a decimal by dividing by 100. So how we got this, for example, is 19.9% divided by 100. So 0.199 times 10, because it has a mass number of 10, and then 0.801, referring to 80.1%, times 11. Adding those together will give you your atomic mass of boron that we see on the periodic table. So the mass number is referring to an individual atom, where the atomic mass is referring to the average in a proportion. Okay, so difference between mass number, which is here versus atomic mass. So representing isotopes. We have different isotopes, so it's important to have ways to differentiate and identify them. So isotopes are written using standard atomic notation. So this is completely new to you, so we're going to walk you through how to use it. The chemical symbol plus the atomic number plus the mass number make up the atomic notation. Potassium, for example, has 3 isotopes. Notice for each of the 3 isotopes, the atomic number is the same as 19. That's what makes it potassium. It is the mass that's changing. So on top, the value is the mass. So for our most common potassium 39, if I'm to write this out, the 39 refers to the mass number, and the 19 refers to the number of protons, which is the atomic number. Looking at table 7.1, remembering that mass number is equal to protons plus neutrons, which is going to be equal to the 39 that's attached to potassium 39. So potassium 39 tells me that it has a mass number of 39, and then the atomic number is 19 based on the periodic table. I can then calculate that 20 neutrons by taking 39 minus 19, meaning there's 20 neutrons in the nucleus. These two sum together makes 40, so potassium 40, and these two together give us our 41. So potassium has 3 isotopes, which we just talked about. Mass always comes from protons and neutrons. So for potassium, the atomic number is always 19. It always has 19 protons. This never changes, otherwise it would not be potassium. For our first example of potassium 39, to get that mass number, it is 19 plus 20 equals 39. So that again is how we got the potassium 39. 19 plus 21 is 40. So that's our potassium 40. And then 19 plus 22 neutrons is equal to 41. So the number of protons and neutrons added together gives us our isotope number, which is referring to this right here. Potassium is found in nature in certain ratio of isotopes. So it's not an even split between these 3 isotopes. We've got 1 really common isotope and 2 less common isotopes. 93% of the world's potassium is potassium 39, so that's the most common. Approximately 1% is potassium 40, and 6.7% is potassium 41. So again, to calculate the atomic mass, based on these mass numbers, we divide the percentages by 100 and multiply them by the mass number. And this, when summed together, will give us our atomic mass of 39.1. I'm just going to make a note here that this is percent as a decimal. So it's percent as a decimal times the mass, and then percent as a decimal times the mass plus percent as a decimal times the mass gives us 39.1, and this is what we see on our periodic table, which is the average of the isotope masses, known as the atomic mass. So because we're talking about potassium, we think of bananas. So the most potassium heavy thing that most people come up with is bananas. So yes, bananas and many other things are radioactive. So tons of things in nature are naturally radioactive. Bananas are super high in potassium. And potassium has different isotopes, some more stable than others. So this is what makes bananas radioactive. Potassium often undergoes what is called beta decay. So potassium 40 is radioactive, and it is in bananas. So a chunk of uranium ore has the same radiation as a bunch of bananas, and that's pretty crazy. This is just different types of radiation. Okay. Radiation exposure in our daily lives. There are tons of different things. Don't worry about sieverts, SV, or microsieverts. We're really just focusing on kind of the amounts of things that you're getting. So what kind of will give you the most radiation. So the breakdown of where things come from, we're not going to worry much about the measurements of sieverts or microsieverts, but different places you go to, you might get exposed to radiation. So if, for example, you get an X-ray, if you live close to a nuclear power plant or work in a nuclear power plant, which are common back east, it's mostly if you work. Living close to it really doesn't matter all too much. But yeah, and then taking a plane is another example. Different foods, there are a ton of different food sources that are naturally radioactive. So yeah, you can pause here and read this in more detail if you're interested. A couple reading check questions for you to read through before moving on to the next lesson. So pause here if you need to and finish these off. And a few more practice problems for you to finish here as well. 2 slides will be placed in a Word doc located on Teams. So that should be linked in the schedule as well. All right, so that is it for this lesson.